All right, so this is in reference to why the image is. All right, so this is one of those problems that you have to do on your own. And hopefully I'm going to get these problems in by the time I give this lecture again next time around. All right, so observation. Why is the image magnified? What causes the image to become magnified? So this is case number 3 that we're looking at. All right, so this time the object is located within the focal length. And then we'll follow the ray diagram rules. The reflected ray is going to go through the focal point. And the ray which is lined up along the direction of the radius of curvature is going to get reflected onto itself. This time, the reflected rays can be extended all the way beyond the mirror. So the point of convergence is going to happen beyond the mirror somewhere, right there. So it happens right there. So the image is going to form behind the mirror. And notice that it's going to be larger. Because it's beyond the mirror, it's going to be virtual. And it's going to be upright. So image is virtual, upright, and it's going to be larger. Once again, using 3 of the rules for the ray diagrams, convergence is going to happen right behind the mirror. So it's going to be, image is going to be larger, it's going to be virtual, it's going to be upright. So that's what we get when the object distance is smaller than the focal point. So the object is situated between a concave mirror surface and its focal point. So the image formed in this case is going to be virtual, it's going to be larger, and it's going to be real. So that's what we have to look for. Real and erect is not the right answer. Real and erect is not the right answer. It has to be virtual and erect. That's the one that makes sense. So C is the best answer in this case. So this is problem number 2 based on that. Once again, this is one of the problems that you may have to try yourself. No, I decided to do this problem. So let's do it together. So object distance is going to be 6 centimeters. So the object is located 6 centimeters in front of the mirror. Focal length is going to be 10 centimeters. So the object is within the focal length. So it's going to give us a virtual image. So locate the object itself. Q is the object distance. And given the height of the object, figure out the height of the image. So image is going to be actually larger than the object. So that's what we're looking for. So this is the formula that we will get to use. So sum for Q. So the Q is going to be the image distance. We do the algebra, isolate Q, so we end up getting 15 centimeters. All right. Notice that there's a negative sign there. So negative indicates that the image is going to be virtual. So it's going to appear behind the mirror. That's what it means. So it's going to be imaginary. So let's figure out the magnification. Obviously, the image is going to be larger. All right, so what do we have here? So this is the image distance to the object distance. This should give us the magnification. All right, so let's figure out the magnification first. So magnification is going to be 2.5. So image is going to be 2.5 times larger than the object. And now let's figure out the height of the image. Plug the numbers in. So image is going to be 3 centimeters. So image is going to be imaginary, upright, and larger. So why parabolic mirrors as opposed to the spherical mirrors that they're using? Notice that they're trying to concentrate the reflected rays onto these pipes. And the problem that they're having, and this is the solution to that problem, is if you're using spherical mirrors, depending upon how far away from the optical axis the incident ray is, notice that now the reflected rays are converging to the same point, so it doesn't have a common focus or focal point. If you end up using parabolic waves, parabolic mirrors, you can actually have all the reflected rays converge to the same focal point. That's the reason why, as opposed to using spherical mirrors, they use parabolic mirrors. And because they're using parabolic mirrors, the reflected rays converge to the same point, and at the focal point, they place these pipes so that they can actually heat up the lamp properly.
In many ways, a radio telescope operates very similarly to an optical telescope in the sense that there's a large collecting area, a parabolic surface that serves as a kind of a light bucket to collect the radio photons, the electromagnetic waves that come in from space. And the parabolic dish then focuses the radio waves into a receiver, which is then recorded these days by computers.
In recent years, there was another American space disaster. This one did not cause any loss of life, though it was a huge financial mess. And it was unusual in another way. It had a happy ending. The Hubble Space Telescope was a bitter disappointment to scientists from the day it was launched. But the Hubble was already in orbit before scientists discovered the main mirror was distorted, producing only about 1/3 the resolution it was designed for. Several things had gone wrong. One, the mirror had been ground to almost unthinkably close tolerances, but in the wrong shape, because its own weight distorted its shape in the gravity on Earth. Once freed of gravity, the mirror sprung into a slightly different shape. Critics say it should have been tested for that.
We have an axiom here. One test is worth 1,000 expert opinions. And this is a classic example where no one could figure out a very elegant way to test it in zero-G, so they didn't.
NASA had two choices. They could abandon the hugely expensive project, or they could send a crew up to fix it. Astronaut Story Musgrave got the job. When he arrived in space, the Hubble was a mess.
Putting in some new rate gyros, which had failed. Putting in the new wide field planetary camera, the deployable optics bench to correct the spherical aberration, new magnetometers. The computer had lost half of its memory, replacing a coprocessor to get the memory back. All of those kinds of tasks, if you added up the total amount of work that we had to do, it came out to 5 days.
At the end of it, the results were better than anyone had dared hope for. Since Story Musgrave's $50 million overhaul, the Hubble Space Telescope has looked farther into space than any instrument in history. A huge, costly engineering disaster that was fixed.
So how did they fix the problem with the Hubble? So that's something that we will get to investigate. So moving on. Why does it look small inside this mirror? What's happening with the mirror? So this is, notice that the objects appear smaller than what they are usually in these mirrors. So the question is why? Why do they look smaller? So now let's focus on the convex mirrors. And notice that these are divergent mirrors. So reflected rays will be divergent. But if you're looking at the reflected rays, and if you extend them all the way beyond the mirror into the virtual space, notice that they will converge to a point. So that once again becomes focal point. And focal point is going to be in the virtual space, the space behind the mirror. So that's what we're looking at. So F is going to give us the focal point distance to the focal point. Once again, is our focal length. And if you double that distance, it gives you the radius of curvature. Ray tracing rules, once again, we will have 3 of them that we're interested in. So the ray which is parallel to the optical axis upon reflection is going to move in such a direction that when you extend it in the opposite direction into the virtual space, it's going to look like it's coming from the focal point. The ray, which is lined up with the radius of curvature, is going to get reflected upon itself. And the ray, which is pointing towards the virtual focal point upon reflection, is going to go parallel to the optical axis. So let's use some ray tracing to figure out what happens to the object itself, what happens to the image of an object. So you got the focal length, you got the radius of curvature. All right, here's the rule number 1. The ray which is parallel to the optical axis upon reflection is going to move in a direction which is going to be lined up with the focal point. So it just gets reflected in that direction. So notice that you got these dashes indicating that this is your virtual space. Second ray, which is lined up with the radius of curvature, is going to get reflected onto itself. All right, so we look at the ray tracing in the virtual space, we end up getting a point of convergence here. So that's where the image is going to appear. So let's use rule number 3, one more rule. Ray which is directed towards the focal point upon reflection is going to go parallel to the optical axis. So what we need to do is we need to extend the reflected ray into the virtual space. All right, so we end up getting the point of convergence right there. So that's where the image is going to appear. So number 1, it's in virtual space, so image is going to be virtual. It's going to be upright virtual, and it's going to be small. All right, so hence the reason why the images generated by inside convex mirrors will be smaller. All right, so they will appear inside the mirror, so which means that they will be virtual. They're going to be smaller, and they will be upright. So here's a problem for you to try. So this is problem number 3. Now let's talk about refraction.
She's just a small town girl with some big town dreams. Someone's getting lucky. Question is, who?
All right, so the lenses, how did they work? Speaking of lenses, how did NASA solve that problem with the Hubble telescope? All right, once again, we have the converging lenses and we have the diverging lenses. Converging lenses are on top, the diverging lenses are at the bottom. All right, so these are concave lenses and all right, so this one is concave. These are the convex lenses that we're looking at. You can take a prism and then obviously shape it into a lens. So the prism, notice that the refracted rays are not converging to a single point, but by just shaping the lens, taking a prism and shaping it into a lens, you can get the rays to converge to the same point. So that point of convergence becomes the focal point. So we will have the same concept. So notice that the rays are converging to a point, so that becomes our focal point. So this is known as the principal focal point at P. Or we can have concave lenses. And once again, you can take a prism and shape it into a concave lens in this case. And then as a result, what's going to happen is the refracted rays will diverge. And if you take the diverging rays and extend them to the space in front of the lens, notice that it's going to look like they're emanating from a point which is known as the focal point. All right, so here's a concave, and then notice that the rays are diverging. All right, so if you extend the diverging rays into the space in front of the lens, they're going to be converging to the same point, or it's going to look like the rays are emanating from that point. So that becomes the focal point. So converging lenses, once again, we will have the rules, 3 rules. So these are going to be our focal points because we're going to have 3 rules. So I'm just setting it up. All right, so rule number 1, the ray which is parallel to the optical axis, upon going through the lens, it's going to go through the focal point on the other side. So it's going to get, upon refraction, it's going to go through the focal point. So the ray going through the focal point upon refraction is going to go parallel to the optical axis. That's our rule number 2. And the ray, which is incident right at the center, pointing towards the center of the lens, is going to go through unrefracted. So this is rule number 3. So those are the 3 rules that we will have for ray tracing. Rule number 1, the ray which is parallel to the optical axis upon refraction is going to go through the focal point. Rule number 2, this is more like the ray which is going through the focal point upon refraction is going to go parallel to the optical axis. And rule number 3, the ray which is pointing towards the center is going to go through unrefracted. All right, so now we can focus on the image formation by a converging lens. All right, so you got the focal length, twice the focal length that we're looking at. So we will place the object outside twice the focal length of the distance. So once again, we will use the ray tracing rule. So the ray which is parallel to the optical axis, upon refraction is going to go through the focal point. The ray which is directed towards the center is going to go right through it. So we find the point of convergence on the other side. All right, so this is the real space that we're looking at on the other side. So it's going to look inverted and it's going to look smaller. So image is going to look inverted. It's going to be real because it's the other side of the opposite side of the lens. So it's going to be inverted. It's going to be smaller. All right, so when the object distance is larger than the radius of curvature, that's twice the focal point. That's what happens. All right, so object distance is going to be larger. And using the ray tracing rules, you will notice that everything's going to converge to this point. So it's going to be inverted. It's going to be small. It's going to be real because you can view the image from the other side. All right, now this is beautiful. All right, this is what we're dealing with. Notice that this is inverted. It's going to be smaller. It's going to be real when you're looking at it from the other side. It's an audio commercial. This is beautifully done. So that's so capturing reality in a film. Obviously, when you capture it in a film, it's going to look smaller. So how does that happen? So that when you capture it on a film, and then it's going to look smaller. All right, so that's the same idea. Once again, the object is going to be located outside of the radius of curvature of the lens that you're looking at. So the image is going to be smaller, it's going to be inverted, and that's how it's going to be recorded on the film. And that's another example of what we're discussing. Problem number 4 is related to this. Once again, that's a problem that you have to do on your own. That's part of your homework. And so let's move on to the case number 2. This time we will place the object between the radius of curvature and the focal point. And then let's do a ray trace and figure out what happens to the image itself. All right, so we follow the first rule, and then we come up with the second rule. So the ray that is going through the focal point upon reflection is going to go parallel to the optical axis. So we end up getting the point of convergence right here. And notice that now we get an image. Once again, it's going to be inverted. It's going to be in the real space. This time, it's going to be larger. It's not that easy to tell by looking at this, but the image is going to be real. It's going to be inverted, and it's going to be larger. All right, so it's like that. All right, so using 3 of the ray tracing rules, we'll find the image here. It's going to be inverted. It's going to be larger. All right, so the application of it is this. All right, watching movies.
Some degree.
All right, so obviously you have a film which is relatively small, and going through the projector, the image is going to get magnified. It's going to be real and it's going to be magnified.